Hello everyone. I'll start off with transducers and measurements, also abbreviated as TMMI. This is one of the modules that is prescribed for your instrumentation and engineering part of the GATE. So before we start off, we need to know what sensors are and what transducers are. What is a sensor? A sensor is a device that senses some kind of a physical parameter. This could be temperature, this could be sound, this could be pressure, it could be flow rate, it could be displacement, it could be one of many things. And what is a transducer? A transducer is a device that converts this output of the sensor into a measurable output. What do we mean by a measurable output? A measurable output is one which is easily displayed, which is easily processed, and therefore this is usually an electrical output. Why is it usually an electrical output? Because we have extensive systems that have been developed for the processing of signals and for the display of signals that are electrical in nature. Okay. So before we start off with transducers, we need to know how these are signal conditioned. What is the meaning of a signal conditioner? So let us see what the basic system looks like. So this is pretty much what a system looks like. You have physical input given to a sensor. The sensor sends its output to a transducer. The transducer converts this output into a measurable quantity, and that is sent to a signal conditioner. What does a signal conditioner do? It compensates for various kinds of errors that might be there. It amplifies the signal, and after proper signal conditioning, the output is usually sent for storage or display. Okay. So before we move on to transducers, we would like to learn a little about one kind of a signal conditioner. And what is this signal conditioner? This is the Wheatstone bridge. You will have learned about the Wheatstone bridge in other modules and also in your school level. But over here we'll revise this Wheatstone bridge because it is one of the most important signal conditioning units that is used with many transducers. So it really makes sense to learn a little about the Wheatstone bridge. The circuit of the Wheatstone bridge looks somewhat like this. So this is what the circuit looks like. Now we will see how to go about analyzing this circuit. So I request you all to take your pen and paper and start working this along with me so that you understand this better. Over here in between the points B and D, we have a voltmeter connected. This voltmeter is meant to measure the output voltage that occurs because of bridge unbalance. We will see what bridge unbalance means. Let us consider that the the voltage source is supplying current equal to I. Now as the current I reaches the point A, it divides into two, I1 and I2. Now voltmeter is an instrument that has high internal resistance. So for the time being, let us assume that the internal resistance is so high that negligible amount of current flows through the voltmeter. Therefore, we can think of this part as an open circuit. So if this were an open circuit, then the current I1 would flow into the arm BC and the current I2 would flow into the arm DC. Okay, they would then again combine at the node C and flow back into the voltage source. So now let us try and write down equations that can help us find the voltage across the points B and D. If we were to compute the voltage at node B, what would that be? It would be this voltage across AC minus the voltage drop across the resistor R1. So that is VB is equal to E minus I1 R1. Similarly, VD would be I2 minus R2. Now what is I1? I'm sorry, the voltage across at node VD would be E minus I2 R3. Please make this correction. So the current I1 and I2 have been found by using Ohm's law. Now the voltage V. The voltage V is the difference of the voltages at node B and D. That is VB and VD. So we get VB minus VD. So let us try and substitute these equations that we've got over here into this equation. So what do we get? we get this. Now substituting the value of I2 and I1 into this equation, we'll try and find what V is. So this is the output voltage V. Let us try and simplify this a little. This is what we get. Now simplifying this further, what do we get? So this is the final expression for the voltage across the terminals B and D. Now suppose that R2 into R3 is equal to R1 into R4. Then what do we get? Then the output voltage V is equal to 0, which is a very interesting result. This tells us that if we can get this product to obey this equation, that is R2 into R3 is equal to R1 into R4, we will not get any output voltage across the Wheatstone bridge. And in this condition, the Wheatstone bridge is said to be balanced. So when we get an output voltage from the Wheatstone bridge, we say that there is an unbalance in the Wheatstone bridge. As long as there is no output voltage, we say that the bridge is in balanced condition. This equation is also expressed popularly as this. That is, when the bridge is balanced, the ratio of the resistances in adjacent arms is the same. So when we talk about Wheatstone bridge, there are two expressions that are very important and that need to be remembered. One is the expression of bridge balance. That is, what is the ratio of the resistances when the bridge is balanced. And second is the expression for output voltage V, which is this expression. So it would be good if you could remember these two expressions, as in GATE you have plenty of problems that require you to use these expressions along with other equations in various problems that are based on transducers. So I hope this makes the concept of a balanced Wheatstone bridge clear. This is one of the most simplest forms of the Wheatstone bridge. There are various other forms of the Wheatstone bridge, and these are known by different names. And what is the difference in each of these? Your resistances are sometimes replaced by capacitors, or they may also be replaced by inductors. In these cases, what happens is that the supply voltage is no longer a DC source but an AC source. Okay. So let us now move on to the various transducers, and let us see what are the transducers that we need to study. So the GATE syllabus prescribes various transducers under the following headings. These are the four main kinds of transducers that we need to study. First is the resistive transducer, then the capacitive transducer, the inductive transducer, and finally the piezoelectric transducer. Of course, transducers are not only limited to these four classes. There are many other minor classes of transducers that are available, and we will study each of those not under a separate heading, but as the case may be in different systems. For instance, we might study some of them while studying pressure measurement. There will be others that will be studied while measuring temperature, level, flow, etc. So let us start off with the first one, that is resistive transducers. Now, under resistive transducers, we will study some of the more popular types in this module, and there will be others that will be studied under the chapter where we are studying various measurements such as pressure, temperature, level, flow, etc. So, some of the transducers that we will be studying now are as follows. These are some of the popular types that we would be studying. The first one, RTD, is an abbreviation for resistance temperature detector. Then we would study thermistors, potentiometers, and finally strain gauges. As I said, these are not all the types of resistive transducers that are available. There are various other types too, but those would be studied under various other modules. So coming to the very first one, that is the resistive temperature transducer. The resistive temperature detector. The resistance temperature detector is one of the simplest kinds of temperature detectors available. The basic principle of this kind of a temperature detector is we have a resistance wire and a constant current is allowed to flow through this resistance wire. So as we know from Joule's law of heating that some kind of a heat would be generated when current flows through the resistor. This heat is given by I squared into R into T. Where I is the current flowing through the resistance temperature detector, R is the resistance of the detector, and T is the time for which the current is allowed to flow through the detector. So when current flows through the detector, what happens is heat is generated. Because of generation of heat, the temperature changes, and this temperature change causes a change in the resistance. So what happens is that if you allow a constant current to flow, then according to Ohm's law, we have, if a constant current is flowing through the detector and its resistance changes, then the voltage across the resistance temperature detector changes. We keep monitoring this voltage, and the change in the voltage is calibrated in terms of temperature. So that gives us a neat way of detecting the temperature. So what does this apparatus look like? Well, it is simply a resistive element which is usually made of platinum. So this could be a simple schematic circuit for the measurement of temperature. What do we have here? We have a resistance temperature detector to which a constant amount of current is supplied through the voltage source E. And we have another resistor over here, R. This is a current limiting resistor. So once we have a constant current flowing through the RTD, as the resistance of the RTD changes, what happens is the voltage across the RTD changes. So because of this change in voltage, we can measure the temperature. Now we need to know a way of calculating the resistance at a different temperature. How is the resistance dependent on temperature. It is this dependence of resistance on temperature is given by a relation, that is a relation that gives you the variation of resistance with temperature, where RT is the resistance at a temperature of T, R0 is the resistance at temperature of 0 degrees Celsius, delta T is a change in temperature from 0 degrees Celsius, and alpha is a constant known as the temperature coefficient of resistance. Alpha is measured in units of degree centigrade inverse. One common mistake that many students make is that they assume R0 to be the resistance at an initial temperature, which is incorrect. The value of R0 is specified only for the temperature of 0 degrees Celsius. So in case you have a problem in which an RTD is said to move from temperature of say 25 degrees Celsius to 50 degrees Celsius, do not mistakenly take R0 to be the value of resistance at 25 degrees Celsius. It is always the value of resistance at 0 degrees Celsius. Now this is called a linear approximation. This is really not the most accurate way of representing the variation of resistance with temperature. In general, the expression goes like this. In general, this is the expression where you have other higher order terms of delta T. But for a linear approximation, all higher order terms are neglected, which is why we are left with this expression. In some problems, you might be required to use a quadratic approximation where this second order term is also used. That is, the three terms, 1, alpha delta T and beta delta T square are used in the problem. So in that case, you would be supplied with the value of alpha and beta and you have to work accordingly. But in most cases, you are only supplied with the value of alpha and therefore you are supposed to assume a linear approximation. Now let us try a simple problem that will explain the concept of a resistance temperature detector. I request you to note down the values of the various quantities that are given in the problem. The question says that an RTD whose resistance at 20 degrees Celsius is 500 ohms, that is has a temperature coefficient of resistance, that is alpha, equal to 0.005 per degree Celsius. we have to find what is the value of the resistance, that is nominal value of resistance at 0 degrees Celsius. That is, we have to find R0. So since the value of alpha is the only value that is given and beta is not given, we assume that there is a linear approximation to the relationship between resistance and temperature. Therefore, we may write R20 is equal to or arranging this to obtain R0. We get this expression. Now in this expression, we are given the value of R20. We are also given the value of alpha. What is the value of delta T? That is change in temperature. The change in temperature is from 0 degrees Celsius to a temperature of 20 degrees Celsius. So delta T is T2 minus T1, that is 20 degrees Celsius. Substituting these values, we would find that R0 turns out to be this would approximately be the value of R0. I would request all of you to do the necessary calculations and verify whether this answer is correct or not. Now we will see another sum wherein we use the concept of quadratic approximation as well as linear approximation and see what the difference is. The question says that there is an RTD whose nominal value of resistance, that is R0, is 102 ohms. Its value of alpha is given as and the value of beta is given as this. Now the RTD is taken to a temperature of 100 degrees centigrade and we are asked to find what would be the error in the computation of RT if we use a linear model as apart from a quadratic model. So the final temperature is given as 100 degrees Celsius. And the initial temperature would then be 0 degrees Celsius. So we have to find two different values of RT for the same rising temperature using different models. Using the linear approximation model, we get and using the quadratic approximation model, we get so these are the two values of the RT that we would get using the linear approximation model and the quadratic approximation model. What is the error that we get? The error would be simply be the difference between the two values that we compute over here. So that would be equal to that would be the error, right? Okay. So for simplicity's sake, let us change this value of R0 to 100 ohms. It will only make my calculations easier. So this gives me an error. The error is equal to please verify if my values, the values that I have substituted over here are right or not. We have R0 which we've changed to 100 ohms. We have the value of beta supplied to us, that is 6 into 10 to the power minus 7, and we have delta T which would be equal to the final temperature minus the initial temperature. That would be 100 degrees Celsius. The square of that would give me 10 to the power 4. So this gives me an error of 0.6 ohms. So which means that if I had used a linear approximation model as opposed to a quadratic approximation model, I would have incurred an error of 0.6 ohms in my value of RT. So if in a particular application such an error is tolerable, then we would go ahead with the linear approximation model as it makes computation easy. If this kind of an error is not tolerable, we need high accuracy systems, then in such applications we would go with the quadratic approximation model. Of course, we would have to take the overhead of extra computation. So let us take a break for a while and try and come back to see how an RTD is used in a signal conditioning circuit. Thank you.